Good evening, everybody. Welcome to another uh, video, another topic of this program. And today we'll be dealing with timers. Beginning with timers. Okay. We actually understand the concept of time, and we know that it occurs in our daily life. Now, let's investigate how timers are important in embedded systems and also in tech fields such as IoT, which we'll discuss later. But first, let's dive a little deep into what timers are all about. Okay, the first point here is painfully obvious. We know timers measure time, but how do they actually do it? Digital circuits run on clocks, and when we say clocks, we're basically talking about a square wave that has a particular frequency. And I've listed some examples here. You can have maybe a computer running at 2.7 gigahertz. The Arduino Uno board that we've been talking about all this time, usually it comes with a 16 megahertz crystal. So it runs at that particular frequency. The crystal makes the microcontroller run at that frequency. So clocks are actually important because not only do they allow the device to operate properly, but they actually synchronize different hardware components. But the measurement of time depends on a particular component of the timers, which are called counters. And what counters do is to basically count the number of cycles in a clock. So far, I've just gone through everything I listed down. So it's time to discuss in more detail. So if you look at this diagram, we have square waves, a square wave of a certain frequency, which I can give it any frequency I want to, but for now, just see it as a square wave, and you can see 3 pulses. Now, we said the counters basically count the number of cycles of the clock. So what do we mean by a cycle? So referring to this diagram, if you look at the square wave, you have 2 sides of the square. You have the rising edge and you have the falling edge. So for every pulse, you have a rising edge, you have a falling edge, rising edge, and falling edge. So between now the time between consecutive rising or falling edges. So this is a rising edge, this is another rising edge. So the time in between these two rising edges is a cycle. And this is a falling edge, this is another falling edge. So the time in between these two is also a cycle. So the counter of the timer basically counts the number of cycles in the clock signal. So that's basically what the counter does. Sometimes some people call timers counters, but it all depends. Sometimes counters are actually parts of timers because timers can perform a lot of functions other than just measuring time. But we don't really have to discuss that here because the most important thing is the aspect of measuring time. So it does that by counting the number of cycles of the clock. So, for example, if the square wave is a 16 megahertz signal, let's assume that the clock is a 16 megahertz signal, and since it's 16 megahertz, that basically means there are 16 million cycles in a second. So what this means is that the counter will count 16 million cycles in 1 second. Okay, but 16 million is quite a big number. So let's assume that we're counting just 2 cycles, because if you look at this diagram here, we have just 2 cycles. And the reason is that we've already counted 1 cycle from this rising edge to this rising edge. Now from this rising edge to this rising edge is another cycle. So we have 2 cycles for this diagram, just 2 cycles. So 1 cycle is basically 1 divided by 16 million second. Well, so that means to count a cycle, it takes the counter this amount of time, 1 over 16 million seconds. So if it's to count 2 cycles that we have there, that's equal to 2 divided by 16 times 10 raised to the power 6, which is 125 nanoseconds. That's actually quite fast. So if you wanted to count for a longer time, you basically just needed to count more cycles. And that is actually what will happen if you were to program the timer on the microcontroller. So let's go to the data sheet to discuss a few things. So let's head over to the data sheet. If you go to the data sheet, we actually have 3 timers. There's timer 0, there's timer 1, and there's timer 2. But for today, I'm going to be demonstrating the simple operation of timers using timer 1. And they've already listed some of the features. It's a 16-bit timer, so that means the counter of this particular timer has a register of 16 bits. So I'm not going to dwell too much on explaining the hardware. I'm going to show you the code, a code that basically blinks an LED at a certain rate, and the rate is determined by the timer. So I'm going to share the code and give some explanations on it. Then I'll go to applications of timers. So in order not to waste time, let's do a little explanation of some things that you should know in order to understand the code, the register description. Okay. Okay. Yeah. So we have the counter register. The counter register. So let me zoom this. So this TCN, C1H, and L, that's basically the timer 1's counter. So the counter is basically what counts the clock cycles, as we stated earlier. And the counter register has a size of 16 bits. So it's a 16-bit counter. So if we want to actually store a value in this register, it has to be a 16-bit value. So if we go back to what we have here, what we have in our rough sheets, remember, for a second, you need 16 million cycles. And 16 million isn't a 16-bit number. It's actually larger than 16 bits. So you can't store 16 million into the register because the register is a 16-bit register. 16-bit register. 16 bits. So that means the maximum value you can have is 2 raised to the power 16 minus 1, which is, okay, that's, I think, about 60 something thousand, I think 65535 or so. Let me confirm. So 2 raised to the power 16. That's 65536 minus 1. Yeah, 65535. So this is the maximum number you can have for a 16-bit number, 65,535. That's what you can actually load That's what you can load into the counter register, because we're using a 16-bit timer. So 16 million cycles, it's not possible to put this inside that register. So that means we need a way to cut down the number of cycles to actually achieve the timing that we want. So for the project that we are going to do now, we want to blink the LED every 1 second. So to blink it every 1 second, we know that we can't actually use 16 million cycles because we're using a 16-bit timer. So what do? There's something called a prescaler. A prescaler basically divides the clock signal. So the prescaler divides the clock. And if we go back to the data sheet, we can find the possible values of prescalers. So to the data sheet, let's reduce this a bit. And let's look for where the prescalers are. So, sorry, should be inside one of these registers, if I'm not mistaken. So, yeah, prescalers. So the clock, if you look at bit 2 to 0, the clock selects. You can see in the description the possible values for the prescalers. So there's a prescaler of 1, there's a prescaler of 8, just look at what I'm highlighting, a prescaler of 64, a prescaler of 256, and a prescaler of 1024. So these are values that you can use to divide the clock signal to give you a smaller frequency that can fit into the registers, depending on the timing that you want. And we want 1 second. So how are we going to achieve 1 second? Let's try the largest prescaler of 1024. So if we have 16 megahertz clock and we configure a prescaler of 1024, that actually divides the clock to a certain value. So let me type this out on the calculator and see what that will give me. So I have 16 million clock frequency divided by 1024. So that's 15,625. Interesting. So that's 15,625 hertz. So that's it. I've divided it into this. So this basically means that what this means is that we have 15,625 cycles in a second. So it means for this 16 bits counter for timer 1, it will count all the way from 0 to 15,624. That means it has counted 15,625 values or cycles. So counting all the way from 0 to 15,624 will take 1 second. So it will take 1 second. So let me go over to the code to show you all I've just explained. So if we go to the code, now I've already defined the number of cycles in a second as 15,625, which means my counter just has to count from 0 to 15,624 for a second to elapse. So all I have to do is load that value -1 into the appropriate register. Oh, okay. Seems I made a mistake. The register that we're actually going to load the value into is not the TCNT1 register. It's the OCR1A register. Sorry. This is the output compare. This is where you'd actually load the counter value, not the other one. The other register that we stated earlier, this one, it's also a 16-bit register, but it's actually what contains the current counter value. So as the counter is counting, the current value will be present in this register. But the limit, what it has to count up to, will be stored in the OCR1A register. So we have to put the number of cycles that we want into this register, and the counter counts up to that value, and the time that we want would have elapsed. So let's go back to the code. So yeah, I'm loading 15,625 minus 1, which means that the timer just has to count from 0 to 15,624. That means that's counted 15,625 cycles of values, which basically means 1 second has elapsed. Other configurations are here, but I don't want to talk too much about them. And in the while one loop, I basically put the code to blink the LED every second. So this first instruction waits for the timer to finish counting, and we configure the timer to reload every second based on this value here. So the timer counts at a frequency of 1 hertz because every second it reloads. So that creates a delay every second. And this instruction here is just to toggle an LED connected to PD6. So the LED comes on, goes off, comes on, goes off. So it blinks every second. So let me go to the simulation to show you how it works. So if we go to the simulation and we run the simulation, you see it comes, it's going to come on, stays on for a second, goes off, then comes on, goes off, comes on, goes off. So every second it continues like that. So the LED is flashing every second. So the timer is responsible for how long it stays on, how long it stays off. And we already programmed it to do that every second. So that's basically how we can configure it to work. So that's just hardware stuff, which might be a little bit boring. So let's go to more applications, practical scenarios. So we've seen basically what timers do, how to configure them, how they work. You can actually write your Arduino code to emulate what I just did. In real life, timers have a lot of applications because, for instance, I mentioned earlier that in tech fields like IoT, timers play a role. Being an integral part of hardware systems such as microcontrollers and microprocessors, for certain operations to occur and to be processed in a timely way, you need timers, and you also need what is called interrupts, which we'll discuss in another video. But you need timers because you would want precision in certain things. For example, let's assume that we have sensors, maybe in a smart farm, or yeah, a smart farm, whereby on the farm, you have sensors that collect data, and the data we're talking about include measurements of moisture, soil moisture, the humidity of the air, um, temperature, and things like that. So the sensors will collect data. Now, the sensors have to send the data probably through a wireless network like LoRa. So they have to send the data to a central hub, or a gateway. So now the hub receives the data. Now it has to make decisions on the data it receives from the sensors. And in order to do it in a timely manner, definitely the timer hardware plays an important role in this. Because once it receives the data and it's about to make a decision that, okay, probably the value of the moisture is too low, it's critical, then something needs to be done. It has to trigger maybe a valve that supplies water to the crops and things like that. So making the decision, being able to act in a timely way requires timers and also interrupts, which I said we'll discuss later. So its own is just, all right, the data is coming, and then it's going to make decisions on the data received. And possibly it's also going to, the hub is going to be sending the data to the cloud, right? And also the sensors, they take readings of these parameters, but they have to do it periodically. So them taking readings periodically, probably every 10 minutes, requires timing, requires the hardware timer. So the timer basically is responsible for the sensors taking the readings at a certain rate, forwarding, then the sensors then forward the readings to the hub. The hub makes decisions in a timely way as well, sends the data over to the cloud for further processing. So I can say that a very apparent application of the timers here is the sensors taking readings periodically. And definitely for the sensor nodes, you are going to have sensors, microcontrollers, and stuff like that interfaced together. So that's just an application area looking at how it is used in IoT. They're not necessarily IoT. There are other areas where timers are used in watches, digital watches. So let's see other applications. Um, digital watches. So you have timers there. Essentially, inside the watch, you're going to have an oscillator that generates the square wave, the clock. And then there's a timer or a counter that basically counts the clock cycles. And with that, it determines the number, the seconds, the minutes, the hours, and whatnot. So, so that's basically another application area of the timers. So you basically want something to happen um, at a precise time. That's why you need the timers. Then um, I wouldn't want to talk too much about the application areas. I would like to discuss them when I'm talking about interrupts as well, because timers and interrupts, they are actually friends. They are kind of like close to each other. But interrupts generally, they're applicable to other peripherals, not just timers. Interrupts, you can use them with GPIOs, you can use them with USARTs, with analog to digital converters, SPI, I2C, so many peripherals. So it's not peculiar to timers, but um, it's just that two of them have their application areas, similar application areas. So I guess I've been able to pass something across today. So in the next videos, we're going to be talking about interrupts, then show you application areas as well, and do basic coding. So I think that's all for today. Thank you. And the code and simulation files will be provided so you can test out what was discussed. And in case you don't understand some aspects, you can let us know so we can put you through. So this is the simulation once again, flashing of the LED every second. So it comes and goes up, and the source code, for the source code, it's right here. So everything is going to be provided for you to go through and test. So thank you.